going on, everybody? Mr. Hanson here at Mr. Hanson414. Today I'm here with another geometry video. We're doing side, 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 triangle congruence. Side, side, side. Let me just double check this mic's all good, because last time I wasted my time. So anyways, we've been working through the different triangle congruences, how to prove triangles are congruent or not. Side, side, side. Sounds like it is. If the sides are the same, if all the sides are congruent, triangles are congruent. So let's hop into this right away. Let me pull up the... Nope. There we go. Alright. So, side, 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 triangle congruence, what does it tell you? That's the essential question. Basically, if three sides of one triangle are congruent to the three sides of another triangle, you can conclude that triangles are congruent. It's pretty simple. You could obviously do all this. I ain't messing with that. So, explain one. Justifying side, 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 SSS. We got some Slytherins, some Parseltongues in here. So you can use rigid motions and the converse of the perpendicular bisector theorem to justify the theorem. In the example, we have two triangles, and you want to, they set it up by saying, okay, we're going to let AB, line segment AB, be congruent to line segment DE. You see the tick mark, 1, 2, and 3. Each one matches with the one that it's congruent to. And you're going to transform the triangle using a translation along the ray AD. Followed by rotation about point D so that AB and DE coincide. So that gets you to that point there. Does a reflection map C to F? That's the question. To show this, notice that DC is congruent. DC is congruent to DF, right? Which means that point D is equidistant from C and F. Therefore, and this ties back to something we talked about before, point D lies on the perpendicular bisector of CE. Where's CE? Of CE. By the converse of the perpendicular bisector theorem. So because EC is equal to EF, point E also lies on the perpendicular bisector of CF. So we get into looking like a little kite, right? Bisector that guy. So since point D and point E both lie on the perpendicular bisector of CF, and there's a unique line through any two points, the line DE is the perpendicular bisector of line segment CF. Long story short, they're congruent, right? So in this example, letter B, we're going to show that these two triangles are indeed congruent. So triangle ABC is transformed by a sequence of rigid motions. We've been doing that for a while to form the figure shown below. Identify them. So what were the sequences, or what were the rigid motions that went into the sequence? You'll complete the proof. Alright, so the first thing that happened is the translation along AP. So where's AP? What? I think that's supposed to be AP. That don't really make sense. But I'm just going to pretend that I know what I'm talking about here, because it's like 10 o'clock at night and I'm getting these done. So y'all going to have to do what you get today. Alright, rotation about P, so that PQ, line segment PQ, and line segment AB coincide. So you notice that they're trying to bring them up so we can get into the bisector stuff, right? If they wanted to prove that, reflection across PQ, so PQ, reflection across PQ. Boom. And then complete the explanation. So guys, like I've been saying, it's not, you gotta do the math, but it's more important if you can explain it. And if the math falls a little short, which we all make mistakes, your explanation's watertight, you're good to go. So because QR is, so let's try and follow this, right? So QR is equal to QC, point Q is equidistant from R or C, right? Put them both. And C or R, right? So whichever order you went. So C, one of the two, right? Therefore, by the converse of the perpendicular bisector, perp bisector, notice how this book tends to build all these things, right? Point Q lies on the perpendicular bisector. So point Q is on the bisector. Perp bisector. What is happening to me? Getting hacked. Alright. Similarly, PR, line segment PR is equivalent to PC. Congruent to PC. So point Q, so point P lies on the perpendicular bisector of line segment RC. Yep. So because 2 points determine a line, the line PQ, so PQ is the perpendicular bisector of RC. So by the definition of reflection, the image of point C, so the image of point C must be R, point R. Therefore, the triangles are congruent because ABC is mapped to PQR by a translation, a rotation, and a reflection. So that's how that cookie crumbled. Alright, can you conclude that two triangles are congruent if the two pairs of corresponding sides are congruent? Explain your reasoning. For example, what do you think? Well, if you have two pairs of sides, that's great, but you don't have an angle or a third side, so no, this is not enough. Two pairs, Air Force Ones is not enough. So, your turn. Use rigid motions and the converse of the perpendicular bisector to explain why these two triangles are congruent. So, AB is congruent to AD, right? So, write that. This is the part of geometry I don't love, but we gonna muscle through it. And CB is congruent to CD. So we can say that point A is equidistant from B and D. B and D. Equidistant. Okay, by the converse, so by the converse of the perpendicular bisector theorem, the line AC is the perpendicular bisector of what? So the line AC, perpendicular bisector of BD. Go for that little kite action. Try flying a kite this summer. It was a little cheap one, and it went as well as you would have expected. So by the definition of a reflection, I'm not going to write no more because it's not going to work. So by the definition of a reflection, point D, point D is the image of point B, right? Reflected across the perpendicular bisector AC. So the reflection maps AC onto AC, therefore these triangles are congruent. Alright, so proving triangles are congruent using SSS. So this, we'd like to do things the challenging way and then find a better way. So basically, if all three sides are congruent, you're good, right? So if we look at this triangle, you'll notice that we have 1.7, 2.3, 2.4, 1.7, 2.3, 2.4. Now the question is, are these congruent? Let's figure it out. So we have one set, one pair, three pairs, we're done. It's that simple. So look at this one. So we have DE, it's 20 centimeters, right? And DE is equivalent to, looks like FG. So these two are congruent, right? So you can write DE, FG, and I'm not going to write any more on that because that's just excessive writing. So DH, where's DH? Right there, right? Yep. Is equal to FH, and they're both 12 centimeters, so they're congruent, right? That's good. And EH is equivalent to GH, and they're both 24, so we're good. So these are congruent. So this triangle is congruent to that triangle, which means they are proven by the SSS triangle congruence theorem. See you around. Y'all thought my handwriting is bad. I have not barely written for a month, and I'll come back tomorrow. Woo. So when do you use the SSS instead of maybe ASA or SAS triangle congruence theorem? So if you know that you have 3 sides and you don't have any angles, just go with the sides. So like, yeah, I mean, it's really that simple. I'm not going to try and complicate it. All right, so take a look here, right? What do you see? Do you see what I see? Those 2 sides are not congruent. So you'd say, line segment MN is not congruent to line segment RQ. So this would be a big no. I should have said pause first, right? So pause before you do this one. So this is one of those set up from there, and it's given, it's congruent, 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 congruent. So now is this congruent? Is this shared side? And you should remember this. We've seen this a lot. This is the reflexive property. Don't reflect on them. Reflex on them. Reflexive property. So you can say GJ is congruent to GJ. Okay. Applying. What the heck is that? If you wear one of those to my class, you are getting roasted. Boom, roasted. Alright, so find the value of x for which the triangles, so you can show which triangles are congruent. Matching triangular dependence for herself and her mom. Oh, how sweet. Alright, so looking at it, right? We got bam, we got bam, we got bam, bam, we got bam, bam. Now, the question is, are these 2 congruent? So, what you would do is you would set in these 2 equal to each other, right? Just like normal. So you get a little 4x minus 6 equals 3x minus 4 action. You solve that, you get x equals 2. Okay. So, if you plug it in, you'll find out that you get 8 minus 2, which is 8 minus 6, which is 2. I always do that, right? And then 6 minus 4, which is 2. So that would be congruent. Congruent. Therefore, by SSS, this is also congruent. I'm going to let you pause and try this one for yourself. Little question to think about before you get too far is, how do you know whether angles in one triangle are congruent to the angles in another? So you know the triangles are congruent by SSS, so you know that the corresponding angles are also congruent because of CPCTC. So again, guys, if you don't have a strong set of notes for this unit, you want to make sure that happens. So Edelin made a design, yada, 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 yada. We got 1, we got 2, we got 3, we got 4. Is this equivalent? So we'll set them equal. Alright. So solve this real quick. That ain't gonna work for me, right? Yeah, this isn't gonna work, correct? So PQ is congruent to MN, yep, and MO and PR, right? So if these are congruent, then if NO were congruent, then yeah, this would definitely be right by the SSS. Now, if you put a 5 in there, yeah, if x equals 5, then put that in the 4, so this would be. So boom, 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 boom. I was tripping because I was like, that's 4, this is 5, but that's not what it was. I forgot I had to plug it back in. Alright, your turn, Craig. Craig got some work. Yeah, you guys can do this. Let me see, take a look real quick. So if you want to pause and try this real quick, go for it. The measure of angle H is going to have to be 30 degrees, right? Because of the triangle sum theorem. That's not so that's good, right? So that we know that. Now, if you look at angle V and angle H, those are congruent. You already know that G and U are congruent, so we have two angles, right? And if we can say that this is congruent to this, then we can prove by ASA that they are congruent to each other. So what you would do is set 8x minus 12 equals equal to each other. You end up getting 3. Plug in 3, you get 12. We'll get, what do you know? So that's 12, that's 12. This would work out. So you would just write that when x is 3, wait, we have a y. Why do we have a y? Don't really care about the y, honestly, but you can tell this has to be 60, so then this, we would set this equal to 60 to figure out y, and y would equal 8. But yeah, that would be ASA. So you notice how we can bring in the other ones. Isosceles triangle isosceles has two sides of equal lengths. We got two sides, but we know we need 3 if we're going to do side to side. If we ask everyone in class construction isosceles that has one side length of 8 and one side length of 12, how many sets of congruent triangles might the class make? Well, at most it would be 2. So you could have 8, 8, and 12 centimeters, or you could have 12, 12, and 8 centimeters, because you need 2 legs to be the same length for an isosceles. So this is a really good opportunity for you to do some reflection and just make sure you understand what's happening here, because you can explain this. Couple little things to add before we go ahead and wrap this up. This practice. So I'll scroll through the practices I'm talking. So 2 triangles appear to be congruent. You know that 3 pairs of corresponding parts are congruent, but you have no information about the others. How can you determine whether they really are? Well, it depends on what you have. So can you make an ASA or an SAS, or can you do SSS? If you have some other random weird combination that for some reason wouldn't work, you are not able to prove that it's congruent. So when do we use SSS? What information? Well, you use it when you have 3 pairs of congruent sides. If you have 3 pairs of congruent sides, then you know that the triangles are congruent as well. There's a lot of solving here, a lot of setting, and really just know when to use what you got. And you may be like, oh, I could do this or this, and yeah, that's going to be the case a lot of the time. But in this situation, just do what comes to you, and make it happen. So thanks for watching, guys. Hit that like button. Hopefully this is helping you. We got one more video to make and we're ready to move on. So I'll see y'all later.